Hello everyone, welcome to this session. In the past sessions, we have already known the forward propagation. So in this session, we concentrate on the backward propagation. So what does the backward propagation do? So in this process, we try to optimize the parameters like the width and bias of the neural network to minimize the loss between or to minimize the difference between the neural network output and the true output, right? So this is the goal of the backward propagation. So now let's see how it goes. Before that, we first review the loss function. So loss function, I think you have already heard of it, right? So we have covered in the MATLAB course of this specialization, as well as in previous weeks, right? We introduced several loss functions for regression and classification. So for loss, the lower the better it is, and sometimes we call it the error function or cost function, or we just simply call it loss, right? Let's see how it works in neural network. So suppose this is a neuron, we have an input I, we have a weight, we have a bias, and then we have an output, right? And this output, let's say, for example, is 0.579. If we are assuming that the ground truth, or we say the expected value, is 1, right? The question is that is 0.579 a good estimation? And how can we quantify this? So this will be described by the loss function, right? So for example, if we say for regression, then I can put some loss function here we have introduced before, like mean absolute error, mean squared error, and the root mean squared error, right? So we can see each of these formulas. So these two we have introduced before, and if you use the root mean squared error, we just put a root here, right? So now after we review the loss function, we can see how can we use it in the neural network training. So we can see this is a neural network example we have just shown in the last session, right? We can have the two neurons in the input layer with the hidden layer and with the output layer, and we have these weights, right? So the last session we have calculated the H1 and H2 and the output, right? So we mentioned the expected output is 0.5. So now we need to calculate the error, right? So error is, let's say, we can calculate it here. So now what I use is O1 minus a target, this 0.5, and I put 0.5 here. So this one we call it the half mean squared error loss function. Why I put a 0.5 here, so this goal is to, because it will be cancelled when we do the differentiation later, right? So this is you will see more details later. Now the key question is to consider, because we want to optimize the W, right? So B is considered as 0 in this simplified example. So the key question, how to update W to get lower loss, to minimize the loss function. How can we do that? This is an optimization problem, and the suggested way is a gradient descent, right? So gradient descent we have covered it in the previous sessions, and you must remember there is a learning rate. So this is the step size. We get a gradient and the opposite direction, so we gradually go to the local minimum, right? So now let's do a brief review. So gradient descent, so we can say that for each point, we have a gradient, right? So gradient is the fastest direction and to go to the minimum, and we use a negative direction of the gradient, and step by step, we go to the local minimum. And the step size in machine learning, we call it a learning rate. So we can see the delta in each step, the W is changed by like this. So it's a minus learning rate multiply the partial derivatives of the error function and the W, right? So this is the way of changing of W. So each step we change this, and we will go many steps to iteratively optimize the loss function. So now let's use this to the neural network. Okay, so there are several ways, right? From W1 to W6. So which one shall we start to update? So we first update W5 or W6 because they are the nearest to the output and the error happens here, right? Then we propagate back to the W1, W2, W3, and W4. So because we different from the direction, when in the last session, we go forward to get this value. Now we update W, we go backward. So that's we call it a backward propagation. So now let's first update the W5. Right? So how can we update it? So before we need to understand how much a change in W5 can affect the total error happened here by calculating the error function or the loss function, right? So this needs the knowledge in calculus. So I can explain it here. There is a chain rule. So we can say that the partial derivative of the error with respect to W5, we can consider it like this. So first item, the partial derivative of the error with respect to O1. So what is O1? O1 is the output of this neuron, right? The output. And then the partial derivative of the output of this neuron with respect to the input of the output neuron. So input here. And then we will have the input of the output neuron with respect to W5. So these three items, we multiply them together, we can describe the change in W5, how it affects the total error, right? So we can see how can we do that. So first one, the error with respect to the output of this neuron. So this involves what? Involves the error function, right? The error function here. So then, using the calculus knowledge, we can get it in the analytical form, and we can get a value. The second that we want to get the output of this neuron with respect to the input of this neuron. This involves what? The activation function. In this case, the sigmoid function, right? So we can also get some analytical result and calculate the value. Third step, the input of the output neuron with respect to the W5. This involves the weighted sum in this step to generate the input of the output neuron. So we can use the calculus knowledge, we get the result and the value. So now what we need to do is to multiply these three values. Then we also multiply the learning rate. So here, to make it simple, I set it to be 1. Then we get the delta 5. Then we can we put a minus sign here to go to the opposite direction. We can get this one. So this is the updated W5. So the previous one minus delta W5, we get this. This is the new W5. So similarly, we can update W6. Okay. So now we will see for the next step, right? So we will go to W1, W2, W3, W4. So we take W1 as an example, right? So how can we update W1? Again, the question is that how much change in W1 affects the total error here, right? So we can again use the chain rule. So we can use the partial derivatives of the error function with respect to W1. We can decompose it to the partial differential evolution as partial derivative of the error function with respect to the output of the output neuron with respect to the input of the output neuron. Input of the output neuron with respect to H1. So H1 is what is the output of the hidden neuron. We can see here, output of hidden neuron. So we can see then we can have the output of the hidden neuron with respect to the input of the hidden neuron, this item. Then the input of the hidden neuron with respect to W1. Then we go to W1 now, right? So we can see this chain, right? So each step, we have the output input, this output, this input, we go to W1. So this is a chain, right? So now let's use this chain. We can see this item and this item together. So this one, we already calculated before, right? So when we update the value of W5, so often we call it the delta 0. So we already obtained it. Then we can see this item, using the calculus knowledge, we can get the answer. So the H1 with respect to IH1, the partial derivative, this all again involves the activation function, right? So we can still do this. Then this one, using we can get this answer. Now we multiply them together, we can use this formula, right? So we can calculate the value of the delta W1. Remember the learning rate is here. Now it's equals to 1. We get this value. Again, we do the same thing, right? The new W1 equals to the originally W1. Go to the negative direction. The delta W1. We get a new W1 here. So we're using the similar method. We can update W2, W3, and W4. Right. So now in this step, all the weights are updated, right? So we can, using the updated weight to calculate a new output. So the new output is here, right? So then with the new output, we can still calculate the error function. Using this one, we can calculate the new error is here. So the previous error is this one. We can see the error decreased, right? And then we can do more iterations to continuously decrease the error, and the error function is optimized, right? So consider after many iterations, so suppose the weights we optimize them to be this value. So I wrote it here. So in this case, the output is 0.5002. So it's very near to 0.5. So the optimization stops. So then these weights can be logged there, and this neural network is trained and can be used for prediction in the next step, right? So in this one is a simplified example. We don't consider B, the bias, we don't consider them, but in reality, we shall consider them. But the method is the same, right? The backdoor propagation and the chain rule, right? So if you are not familiar with the calculus, you don't need to really understand how these formulas are provided. But the key thing is to understand how do we optimize the W's and how the chain rule, which one is related to which one, right? How did we propagate from the error to a certain W, right? So, okay, that's all for this session. Thank you very much. Bye-bye.